Okay, let's get started with new lecture material. Oops, let me zoom my camera. There we go. Okay, starting a new semester, new material. This semester we're starting with functions. Functions, what's a function? So before we jump into what exactly a function is, let's remind ourselves of a relation. You've been doing a ton with relations so far. One of the things you've been doing with relations is classifying them as reflexive, irreflexive, symmetric, anti-symmetric, that kind of thing. So what's a relation? It's just a set of ordered pairs. That's all a relation is. It's a set where everything in the set is an ordered pair. Good?
Yeah.
So a relation is just a special type of set. It's a set where everything is just an ordered pair. What's a function? It's now going to be a special type of relation. Okay? So for sure, a function is a set of ordered pairs, and that's going to have a property. And that's what function is going to be. So let's get down to the exact definition. So remind ourselves, relation, just a set of ordered pairs. Okay, so now a relation f is called a function, provided that, remember, it's a relation, so it's a set of ordered pairs. So the special relation is called a function, provided that if you have A paired to B in F, and you have A paired to C in F, B and C have to be the same element. Anything, once you pair A to something, A can only ever be paired to that same thing again. I can't pair A to two different numbers, otherwise it's not a function. Or the other way you've heard it is every left-hand element has to have one and only one right-hand element. So if A is paired with B and A is paired with C, B and C have to be the same thing. We can't pair A to two different things. Let's go over some examples. So here's three relations, F, G, and H. We're going to classify it as function or not function. Okay? So let's look at the top one. Function or not function?
Not function. Should be a function.
But we have -1 there, -1 there.
Okay, but they're not.
But they're not the same number.
Oh, is that negative?
Yes. I thought that was 4.
Yeah, they're not both left-hand elements. 0 is only ever paired to one thing, namely 1. 2 is only ever paired to one thing, namely 5. 3 is only paired to -1. 4 is only paired to 4. -1 is only paired to 7.
What is 3 and -1 and -1 and 7?
Now, so when 3 is a left-hand element, it's always paired with -1. I never had 3 as a left-hand element showing up in here again paired with something
Switch the
else.
sides and have it be a different function. Like switch the positions and have it be a different function.
Yes, that would change the function completely if I swap those two elements.
Oh.
That would change the relation completely. If I swap those two, if I replace this with a -1 and a 3, this is now no longer a function because I have -1 goes to 3 and -1 goes to 7.
So the entire thing in brackets is a function because everything within it is.
So now this relation is not a function because I have -1 paired with 3, -1 paired with 7, but 3 and 7 are not the same number.
Yeah.
Now, if I put it back like this, 3, -1, now this entire relation F is also a function. So F is always a relation. The only question is it also a function? And it's a function that has this property. Let's look at G. G is obviously a relation, it's a set of ordered pairs, but is it also a function? No, why not?
Because the 5 is 1, the 5 is 2.
I have 5 as a left-hand element to 1, and 5 as a left-hand element to 2. Those are different things. G's still a relation, perfectly good relation, but it's not a function. So function, not a function. What about this?
Yes, it's a function.
Yep.
Wait.
Yeah.
Well, yeah, it should be. Yeah, it is.
It is?
Yeah.
Yeah.
I have 1 showing up as a left-hand element 2 times.
Yeah, but 2 is equal to 2.
Yeah, but it's always paired to 2, so we're good.
Yeah.
If I replace that 2 with a 3, then we're suddenly
Not a problem.
not good. Right?
Yeah.
Okay. Question, how many elements are in H?
3. 3.
4.
Come on, you guys not count? 1, 2, 3, 4, obviously.
No, it's 3.
No, it's 3. Why is it 3? Because duplicates don't matter in sets. This element and this element are duplicates. So this is the exact same thing as this. I didn't change anything. Okay? So there we go, thinking about functions from their actual definition rather than the way you're used to pictorially thinking about it. we have special notation for functions. When I say f of a is equal to b, this is saying that b is the right-hand element of a in f. This is saying that the ordered pair AB is in F, where A is the left-hand element and B is the right-hand element. That's what it means to say f of a is equal to b.
Can you repeat that?
Yes. So, when I say the ordered pair A and B is in F, A is the left-hand element, B is the right-hand element. This is another way to say that. This says the left-hand element of A in the function f is b.
Oh, okay.
So let's practice this. Here's f as a function. Here's f as a function. 0 is the left-hand element of what in f? 1. 3 is the left-hand element of what in f? Negative 1. Negative 1, it goes to 7. 2 goes to 5. So that's what that notation means. This is just saying the order pair 0, 1 is in F. The order pair 3, negative 1 is in F. The order pair negative 1, 7 is in F. The order pair 2, 5 is in F. That's all that's saying. Okay? Let's start with G. What's G of 1? 5. What's G of 2? 5. What's G of 3? 4. What's G of 5?
Yeah, well, that doesn't work out.
Is G of 5, does 5 go to 1 or 5 go to 2?
Well, it's not a function.
You can't say. So it's not a function. So you're not supposed to use this notation for just any relation. You're supposed to only use it for functions. So when f is a function, then we can use this notation. If it's not a function, don't use the notation. So we don't use that notation for relations in general. Make sense? Okay. Now let's try and connect this to the way that you're used to thinking about functions. We'll do it for all of them. We won't worry about that. Well, shouldn't erase that. Integer. Oh well. Okay, let's look at this really quick, this relation here. Looking at this relation, what is in this relation? So first off, I'm trying to write out an infinite relation for you. There's an infinite number of things in here. I can't write them all out. Not enough chalk. So here it is. Dot, dot, dot. Negative 3 goes to 9. Negative 2 goes to 4. Negative 1 goes to 1. 0 goes to 0. 1 goes to 1. 2 goes to 4, etc. Do you see the pattern? What's this doing? The right-hand element is always the left-hand element squared. What's negative 3 times negative 3? 9. What's negative 2 times negative 2? 4. What's negative 1 times negative 1? 1, etc. You see
Can
it?
you go back a little?
So here I'm just writing out some function. And it has an infinite number of elements in it. I can't write them all, so I need you to see a pattern. So that you know everything in the function. And so the function is, notice that the right-hand thing is always the left-hand thing squared. Negative 3 times negative 3 is 9. 1 times 1 is 1. 2 times 2 is 4. So question, is this, if I were to write this out forever, would I eventually write this term? 6 comma 36.
Yeah.
If I kept going, would I have eventually written that?
Mhm.
Yes. So you now know, you have intuition for what this function is. And if I were to ask you something like f of 8, what is 8 paired with in this function? 64. Perfect. So you're seeing the pattern. Now, we don't want you to have to rely on a pattern to know what a function is. I can't just say to you every time, trying to figure out what my pattern is here. We need a way to actually write this so that we know exactly what it is. So you're not guessing at a pattern. So how could I write this infinite function? Well, we can use our set builder notation. I can say this is a set of all ordered pairs x, y, where x and y are integers, and y is equal to x squared. The right-hand thing is equal to the left-hand thing squared.
Yeah.
Repeat that.
So this function, just rewriting it a different way.
Yeah.
It's all the ordered pairs, x, y, where x and y are both integers, and y, the right-hand element, is always equal to x, the left-hand element, squared.
Okay.
So here's a way of writing that so we don't have to try and write infinitely many terms.
Yeah.
That's hard to do. Now you notice all you really cared about here was the pattern we were using to get from the left-hand element to the right-hand element. And so it's very common that we represent this as just a function, f of x is equal to x squared. What does this say? This says the right-hand element of x is x squared. The right-hand element of 8 is 64. The right-hand element of x is x squared. And this is how you've been writing functions all throughout your algebra course. That's what you were saying. With me so far?
Yeah.
So it was just a shorthand way for writing down these infinite functions. But all the times you've been working with functions, you've been working with infinite sets of ordered pairs. That's what you've been working with. You just never had them shown to you this way before. So that's all it was, and that's where that notation comes from. Good so far? Okay. Now, more terminology that you've likely heard before. Intuitively, what's the domain of a function? You heard about domain and range? What's a domain?
What you can put into the function.
It's everything you plug into the function. And the range is everything that comes out of the function, is likely the way you've heard it. That ringing bells?
Yeah.
I mean, the words are, but they're not really making sense.
Okay, let's go over it explicitly now. What exactly is the domain of a function? The domain of some function f, which we write dom f, that's the way we'll talk about its domain, you'll get used to that notation, is a set of all the first elements in the ordered pairs of f. Or in other words, it's a set of all the left-hand elements. Let's scribble this down really quick as an example. I didn't really leave myself much scribble space. Ignore that example up there for a second. But let's look at this function f and tell me the domain of f. So here's a function f. What is its domain?
0, 1, 2.
So here's some function f. With me?
Yeah.
What is a domain of f? It's going to be the set of all the left-hand elements. So what shows up as a left-hand element? 0 does. So 0 is going to be in my domain. What else does? 2. What else does?
3, 4, -1.
Is that it?
Yes.
Yes. So there is a domain of this function f. The set of all the left-hand elements. Good? So that's what the domain is. The domain of a function written dom f is the set of all the first elements in the ordered pairs of f. The first being the left-hand one. Similarly, the image or range. Now, I don't know why this is the case in math. Very annoying that we have two words for the exact same thing. Image and range are going to be one and the exact same thing. Unfortunately, all more advanced math textbooks have pretty much all settled on the word image, and all elementary ones have settled on the word range. And it's very annoying. We will not be talking about ranges in this class. We will be talking about the image of a function. But it means the exact same thing as a range. Annoying, but that's the way it is. So the image of a function f, written mf for the image, is a set of all the second elements in the ordered pairs of f, or all the right-hand elements. So once again, if f is our function here, what is the image of f equal to? Looking at this is our example.
1, 5,
The
-1.
set.
The set containing 1, 5, what else?
-1,
-1,
4,
4,
and 7.
and 7. It's the set of all the left-hand elements. Okay. So there's image, there's range. Or sorry, all the right-hand elements. We will no longer use the word range. From here on out, we will use the word image. Not range. Image. Same thing, though. Okay. In more concise notation, what is the domain of any function f? F now is just a stand-in for any general function. It's a set of all the a's where there exists a b such that a goes to b in f.
Restate that, please.
Yeah. So if you have a comma b, if this is an ordered pair in f, then a shows up in the domain.
Yeah.
Similarly, if you have a comma b in f, then B shows up in the image.
Okay.
That's all it's saying. So what's the domain of F? It's a set of all A where there exists a B such that B is paired with A. If there exists some B that A is paired with in the function, A shows up in the domain. If there exists a B such that A maps to B somewhere in the function, B shows up in the image.
Okay.
Good? Okay. Next definition. Let F be a function let F be a function and A and B be sets. Then, how do we read this?
F from A to B.
F is a function from A to B. One of the ways we think about functions is mapping numbers to different numbers. So F is a function from A to B, provided that the domain of F is equal to A, and the image of F is a subset of B. This is easier to understand, I think, if we draw it out pictorially. So let's draw it out pictorially. So looking here, A is a set, -1, 0, 2, 3, 4. So drawing out A pictorially as a set now. Here's B, here's A again, here's another B. So just drawing out sets. F, looking at our function F, what does it pair -1 to?
7.
You see it pairs -1 to 7?
Yeah.
So I'm representing that with an arrow like this. So I'm just drawing out the function, but now more pictorially rather than the set of ordered pairs.
Okay.
So picture to help your intuition. What does it map 0 to?
1.
1. What does it map 2 to?
5.
5. What does it map 3 to?
-1.
-1. What does it map 4 to?
4.
Okay, so here's one way that you can think about F. Right?
Yeah.
So if A is this set, -1, 0, 2, 3, 4, and B is the set 1, 5, -1, 4, 7, then F is a function
Maybe.
from A to B.
Okay.
What does it mean for it to be a function from A to B? It means it maps everything in A to something in B. It means that the domain of F is a set A, so all its left-hand elements are right here, and all its right-hand elements are a subset of B. All its right-hand elements show up somewhere in B. Let's say instead I had A was a set -1, 0, 1, 2, 3, 4. So I just added 1. And B was a set -1, 0, 1, 2, 3, 4, 5, 6, 7.
Okay.
Once again, let's look at F. What does F map? How does F map? What did it do with -1?
7.
-1 went down to 7.
Mm-hmm.
So -1 went down to 7. 0 went to -1.
No, just 1, right?
0 goes to 1, sorry.
Oh, 0 goes to 1. Oh. That was a 1.
3 goes to negative.
Alright, 0 went to just 1. 2 went to what?
5.
5. 3 went to
-1.
-1. And 4 went to
4.
4. Okay, here's another way that we could have drawn, or sorry, if A was this set and B was this set, here's F's mapping from A to B.
That'll be a problem.
You with me so far?
Yeah.
Did we use all of A?
No.
What did 1 map to?
9.
What does F map 1 to?
Doesn't matter.
It doesn't. So if this was our set A and this was our set B, F is no longer a function from A to B. F is only a function from A to B if it maps everything in A to something in B. So if this was my set A and this was my set B, yes, F is a function from A to B. If this was my set A and this was my set B, F is no longer a function from A to B.
So it can be a function if there's leftover numbers in B, but it can't be a function if there's leftover numbers in A.
Perfect. So if A were instead -1, 0, 2, 3, 4, and B were this, now it is a function from A to B.
Mm-hmm.
So I'll say this 1,000 times, but I'll say it again. When is F a function from A to B? When it maps everything in A to something in B. One more example. What happened if I got rid of -1 from B? Now it doesn't work anymore because 3, -1 doesn't show up there. F maps 3 to -1.
Right.
So if this were my set B, F is now not a function from A to B. It needs to be able to map everything in A to something in B in order to be a function from A to B.
Yeah.
Make sense? Okay. So, just give us some examples now. Where's my, over here. Let's look at functions that you know and love coming from your calculus, or not your calculus, your algebra classes. So back in algebra, you had a function, something like f of x equals the absolute value of x. There's one you worked a lot with, right?
Yeah.
Now, to be more explicit, here's really the function you were talking about in your algebra course, but the teacher didn't want to show you this part because they didn't want to confuse you. So, what exactly was that function? It's a function f from the real numbers to the real numbers by f of x equals the absolute value of x. And algebra, since you were always working with the real numbers, this part was just understood and your teacher never told you that because they didn't want to scare you.
If you wanted, you could write a whole set building notation for that, couldn't you?
Yeah.
Sure, yes. But this shorthand, if we're going to use this shorthand, we need to specify
What you're mapping from?
what you're mapping from, and, well, you don't have to specify what you're mapping to. It can kind of be inferred, but helps.
Right. Okay.
Okay, so let's look at this function. F is a function from the real numbers to the real numbers by f of x equals the absolute value of x. Question. What is the domain of the function?
Real numbers.
It's all real numbers. What are all the numbers I can plug into this function and have it work?
Basically all
Any of them. Give me a real number I can't take the absolute value of.
of them. Well, all the other
What's the absolute value of -3? What's the absolute value of 0? What's the absolute value of 100? So you can plug anything in there. But we instantly know that the domain is all real numbers because it's a function from the real numbers to something. If I said over here, f is a function from A to B, what's the domain of f? It's A. It has to be A. Because if f is a function from A to B, it has to map everything in A to something in B. A has to be all your left-hand elements. Otherwise, the notation doesn't make sense. So, on all real numbers, the domain is all real numbers. Now, what is the image of this function? What are all the outputs you get from the function?
all positive numbers including 0.
Yeah, what's an output you can't get? You can't get something like -2. What number can you take the absolute value of and get -2? You can't. Let's go back to when you graphed this function. Do you remember what it was like when you graphed the function? So we're going to graph the function absolute value of x. What's the absolute value of 0? 0. What's the absolute value of 1? 1. What's the absolute value of 2? It's 2. What's the absolute value of -1? 1. What's the absolute value of -2? 2. And so when you graph it, it makes this V shape. That's what you saw in your algebra classes. The graph of the absolute value function. You with me?
Kind of.
You didn't do that in your algebra classes?
I did, but I don't know how we got here.
So you take a number and you...
Okay, I'm more confused on why we can't use negative ones in the second part.
So the question is, how we can plug negative numbers into this function. I can talk about the absolute value of -2 is 2. So f of -2 is 2, because f is just the absolute value function. You with me? So -2 goes to 2. What can I plug in now to f to get out -2? How do I get -2 as an output? What number can I take its absolute value of to get -2? You can't, because when you take the absolute value, it only gives you positive numbers. Or in other words, when you did your graph here, we never came down to -2.
So how we knew was, because I was confused because the
From the real numbers to the real numbers.
But remember, it only maps.
They're both the same, so I was confused. But
They're
do
both
we
the
know
same.
because in the fx equals absolute value, you put the first one in the parentheses and you put the second one in the absolute value?
No. So this function mapped from the real numbers to the real numbers, right? All we were doing is looking at all the outputs you get from this. What are all the things that you can get after you take an absolute value? What are all the possible numbers you can get after you take an absolute value? Just a positive, starting at 0. You could also get 0. Absolute value of 0 is 0. So, have you guys seen interval notation? That's 0 to infinity are all the numbers you can get out of it. With me?
No, not really. I still don't get it.
This is just an example of a function that you use in school where you could plug in any real number, but your output was only going to be half the real numbers.
You're saying exactly what I said,
Okay.
but you said no to it.
All right. If that is what you're saying, then yes, that's correct. So what you need to notice, this is the only thing you need to notice, is that the image of our function is a subset of the real numbers. We did not use all the real numbers. You have to use all the real numbers for your domain. You do not have to use all the real numbers for your image to have a function from the real numbers to the real numbers. That's all we're saying. So if f is a function from the real numbers to the real numbers, what are our inputs? Our inputs always and forever have to be all the real numbers. What are our outputs? A subset of the real numbers. Maybe all of them, maybe not all of them. So the absolute value function is an example of a function that does not spit out all the real numbers. So it is still a function from the real numbers to the real numbers. That's true. But all that its outputs is just a subset of the real numbers. That is why we do not require it to equal b. b just has to include all the outputs. It doesn't have to be all the outputs. And so if your function is the absolute value function, all its inputs are all the real numbers, and all its outputs are a subset of the real numbers. In this case, not all the real numbers.
But we base that on the fx equals absolute value of x.
Yes, we had to use.
That's literally what I asked.
Okay.
You said no. That was so confusing.
All right. If that's what you mean, yes.
Okay, thank you.
Okay. So yes, you have to look at the function to know. That is correct. So let's look at another example, and hopefully this makes more sense. So this time we're going to look at the function from the real numbers to the real numbers by g of x is equal to x squared plus 5. So here's our function. So first off, what is the domain of g?
All the numbers.
What are all the things I can plug into that function?
All the numbers.
Any real number, all real numbers. The domain is all the real numbers. Anytime I have a function from a set, that set has to be your domain of your function. Now, once again, what is the image of g? What are all the outputs I can get?
All the numbers. Right. No, that's correct.
What can I plug into x to get 0 to come out?
Negative 25.
Nothing.
Nothing. Yeah.
Nothing. So I cannot get 0 to come out of this function.
Right, so it's all the real numbers from 5 onwards.
Yeah.
I can get all the real numbers from 5 onwards. I can get 5 up to infinity, and those are the only ones I can get.
Sorry, I didn't do
Why? If I square a number, it's always going to be 0 or positive. So when I take something that's 0 or positive and I add 5, the smallest thing I'm ever going to get is 5. Or,
Well, never mind.
Or the way you've seen this pictorially is, what is this? It's a parabola that's shifted up 5. 1, 2, 3, 4, 5 starts right there, and then you have your parabola. And so your parabola never gets lower than 5. Good?
Yes, but why do we do the bracket and then hence?
Oh, the bracket means included. So that's just interval notation. I'm not sure if you're used to that. Interval notation. This is a shorthand way of writing. It's a set of all x where 5 is less than or equal to x is, oh, that's it. So basically all the numbers in x greater than or equal to 5, including 5. If I want to say just all the numbers greater than 5, we would use a parenthesis over here, which means don't include the 5. In our case, we wanted to include the 5, because when we plug in 0, we can get 5 as an output. But any way you want to say it, I could have just written all the numbers greater than or equal to 5, and written that out in words.
Okay.
And that's perfectly fine as well. That's all that interval notation says. Good?
Wouldn't it also work to do parenthesis 4, comma, into parenthesis?
No. Why does this not work?
Because we're doing all the real numbers. Which
Because this would include something like 4.1, which we can't get 4.1 to do that. Good question. Yeah, but interval notation, typically it's understood we're talking about on real numbers. So 5 to infinity, including 5.
Really?
Yeah. Or the picture you guys did in grade school. Something more like this. You would go 1, 2, 3, 4, 5. You would do a filled in dot with an arrow pointing that way. And if you didn't want to include the 5, you would have done an open dot with the arrow pointing that way. Something like that's what you did. Okay, same thing. Okay. Now, let's do a little bit of counting. Let A be the set, A, B, C, D, E, and B be the set, 1, 2, 3, 4, 5, 6. So we got 2 sets. With me so far? How many functions f can we make from A to B?
Okay.
How many ways can I create a function from A to B? Now, remind ourselves, what does it mean if it's a function from A to B? What does our function do?
Everything in A has to match with something in B.
Perfect. It maps everything in A to something in B.
So we can have 5 functions.
So whatever our function is, it has to map A to something. It has to map B to something. It has to map C to something. It has to map D to something. It has to map E to something. That's what it means for it to be a function from A to B. It has to map everything in A to something in B. What's one possible function we have? Well, I can map A to 1, B to 1, C to 1, D to 1, E to 1. There's one possible function from A to B. I map everything in A to something in B. All right, so there's one that I could have done. How many possible functions
So that's
from...
allowed?
Huh? Yeah, I can map them all to the same thing. That's perfectly fine.
Is it?
Going back to grade school, that's what you called a constant function. When you said f of x equals something like 2, how do you graph that? Just 2 across the board. Everything goes to 2.
So B can be the same throughout all of them, but A has to be different.
Yeah.
Correct. Every left-hand element needs to go to one and only one right-hand element.
Okay. Okay.
So, mapping A to, I could also have done A goes to 1, B goes to 2, C goes to 1, D goes to 2, E goes to 1. There's another thing I could have done. I map everything in A to something in B. How many different functions can I make like this?
Is it 6 to the 5?
Is it 6 to the 5?
Or...
6 options for the first one, 6 options for the
Yeah.
third one.
Perfect. So my function has to have this form if it's a function from A to B. It has to look something like this, right? So now the question is, how many things do I have for how many options do I have for what I compare A to? 6. How many options do I have for what I compare B to?
Also 6.
6. For C? 6. D? 6. E? 6. And so if I have 6 for that, and 6 for that, and 6 for that, and 6 for that, and 6 for that, that's 6 times 6 times 6 times 6 times 6 options. What's our short way of saying 6 times 6 times 6 times 6 times 6?
6 to the 5.
6 to the 5. So there are 6 to the 5 options. There's 6 to the 5 ways I could have done this. Now,
That makes sense.
what would it have been if instead I would have said, A here only has 3 elements. So what if A would have just been ABC like that?
And it would have been 6 to 3.
Then it would have just been 6 to the 3,
Such as B to the A.
right? On the other hand, what if B here has only 4 options?
And B 4 to 3.
Then we have 4 for that, 4 to that, 4 to that, and we get 4 to the 3. in general, if our set A, if the size of our set A is equal to little a, and the size of our set B is equal to little b, how many options do we have here?
B to the A.
You get to choose from our set B, A times, however many things you have in A. So in general, it's B to the A. If B has 4 elements, 1, 2, 3, 4, and A has 3 elements, 1, 2, 3, then it's 4 to the 3. That makes sense? Okay, so here's our first little theorem, and that's all it's going to say is exactly what we just said. Let A and B be set such that the size of set A is little a, and the size of set B is little b. Then there are B to the A functions from A to B. You've already got the intuition for it. Now we're going to go through a quick counting proof. Okay. 1. Relabel the elements in the set such that A is 1, 2, 3 all the way up to little a, and B is 1, 2, 3 all the way up to little b. What do I mean by that? So A here we had the set A, B, C, D, E, right?
Yeah.
I'm saying let's relabel this set A so that it's just a set 1, 2, 3, 4, 5. Just relabel it with numbers. Because I have no clue what's in the set A. Could have been anything in there. I'm just relabeling it in there. I'm just going to say, whatever the first thing is in the set, I'm going to call you 1. It'd be like if you guys are in this class, didn't know your names, I said, from here on out, I'm going to call you 1, I'm going to call you 2, I'm going to call you 3, I'm going to call you 4, I'm going to call you 5, I'm going to call you 6. It doesn't change anything. You are still what you are. It's just a label I'm applying to you. So just relabel big A. So that's just 1, 2, 3, 4, 5, all the way up to however many elements there are in there. In this case, what's our size of A?
It's 5.
5. So we did all the numbers 1, 2, 3 up to 5. If there's 6 people in this class and I gave you each a number, then the last person would get the number 6.
Right.
So relabel everything in A, 1, 2, 3, all the way up to little a. Since there's little a things in big A, then we'll label everything. Good?
Mm-hmm.
Similarly for the set B, just relabel it 1, 2, 3, all the way up to B. Just so I have names for the elements in the sets. Good so far? Okay, now I'll do exactly what we set up there. Observe then that any function f from A to B must have the form 1 goes to something, 2 goes to something, 3 goes to something, little a goes to something. It has to have this form because if it's a function from A to B, it has to map everything in A to something in B. So 1 has to go to something, 2 has to go to something, 3 has to go to something, little a has to go to something. Good? Okay. Observe that for each of the A order pairs up here, there are B ways to finish it. Pick an order pair. How many options do I have for what comes next?
However many of these are in B.
Anything in B. I can pick anything out of B for what goes here. How many things are in big B?
Little b things.
Little b number of things. So I have little b choices for what goes there, little b choices for what goes there, little b choices for what goes there, little b choices for what goes there. In our concrete case that we first did, 1, 2, 3, 4, 5, 6, little b was equal to the size of B, was the size of big B, which was 6. And little a was the size of big A, which was equal to 5. And so the first time we did this, what did we say that it was? 6 to the 5 options. Same exact thinking. Except for now, instead of using 5, I'm now using little a, and now instead of using 6, I'm using little b. The exact same thinking. We're just doing it in general now. So for each one of those order pairs, I have B options for what comes next. So I have A order pairs with B options for how to finish each one for a total of B times B times B, A times. That's it. Exact same thinking we set up there, just trying it out more general. Good? Okay. Now, let's remind you of this inverse notation that we had for relation. If this is my function f, sorry, not my function. It is a function, but just think about it as a relation. What is f inverse? What is the inverse of a relation?
It's where you swap all of
It's just where you swap all the terms in the ordered pairs. So this would just be 1, 0, 5, 2, negative 1, 3, 4, 4,
7, negative 1.
comma 7, negative 1. That would be F inverse if that was F. So when you have a relation, what's the inverse of a relation? Just swap everything in the ordered pairs. I intend to press to write it down here so I didn't have to squish it there. So tell me what to write for F inverse.
1, 0.
1, comma 0.
5, 2.
Negative 1, comma 3. 4, 4, comma 4, and then 7, comma negative 1.
All right, let's move to G. G is a relation, so we can take its inverse. So what's the inverse of G?
5, 1.
Sorry, what?
5, 1.
That's a 0.
What?
Wait, sorry, I was on the wrong one. I'm sorry.
Okay.
1, 5.
1, comma 5. Hard to write this close to the chalkboard or top tray.
5, 2.
5, 2.
2, 5.
2, 5.
4, 3.
4, comma 3. All right, there it is. The inverse, just swapping all the ordered pairs. We have everyone.
Excuse me. Well, hallelujah. Good morning. It's good to see you. Have a good day.
So that's all the inverse is. Nothing tricky to it. Just swap the order of the ordered pairs. That's all. An inverse function is going to do the exact same thing. So when we talk about an inverse function, it's just a function where you swap all the ordered pairs. And it still happens to be a function. It still follows the rules of a function. So that's what we're working our way up to.
Isn't the case for every function, right?
It will not be the case that the inverse of a function is a function. Maybe as one example of that, let's quickly do h here. So get rid of that. Let's look at h inverse here. What is h inverse? Notice h is a function. H is a function.
Yep.
1 only goes to 2, 3 only goes to 2, 1 to 2, 2 to 3. So it's a function. Let's look at h inverse. What's in h inverse?
2, 1.
2, 1,
3, 2, 3.
2, 3,
2, 1.
2, 1 again, but we don't need to write that, and then 3, 2. Notice that 2 goes to 1, 2 goes to 3, not a function. So just because h is a function does not mean h inverse is a function. Notice that this wasn't adding anything, so get rid of that. That's not doing anything. It's just a repeat of this. 1, 2, 1, 2 again doesn't change anything. Is that throwing you off?
Yeah, a little.
Okay. Let's pretend h is just this function. 2, 3. There we go. So here's h, and it's a function. 1 only ever goes to 2, 3 only ever goes to 2, 2 only ever goes to 3. Now here's its inverse. I just swapped those. The inverse is no longer a function. It's still a relation, it's just not a function anymore. What does 2 go to in this function?
Oh, I didn't catch that. I'm sorry.
Okay, there we go. So you see it? So a function took the inverse, not a function. F here was a function. When we took its inverse, it was still a function. So it's very special functions that once you take their inverse, it's still a function. Not every function, when you take its inverse, is going to give you a function. Some will, some won't. Okay. So, move the camera before we talk about it. Talk about the property it needs to have so that when you take its inverse, it's still a function. No, it just needs to be 1 to 1.
Just 1 to 1.
Almost. Yeah, basically. Okay. So a function f is said to be 1 to 1. Now no one ever writes out 1 to 1 like that. Everyone writes 1 to 1 as 1 dash 1 for 1 to 1. So that's the way I'll write it from here on out. But that's what it means. A function f is 1 to 1 if, when you have a paired with c and b paired with c, a and b are the same thing.
Repeat that like exactly as I said it, but slower.
If a and c are in f, and b and c are in f, then a and b have to be the same thing. So in order to have a function, each left-hand side had to go to one and only one right-hand side. In order for it to be a one-to-one function, each right-hand side has to be paired with one and only one left-hand side. So h here was not one-to-one because I have 1 goes to 2 and 3 goes to 2. I have two different numbers going to the same thing, which means it's not one-to-one. One-to-one means two different numbers will always go to two different things. Or, in other words, if two numbers go to the same thing, they better really been the same number.
Oh, okay. That makes sense.
You can think about the contrapositive of this. If A is not equal to B, then that would imply that, well, that's a harder way to say it. Now, here's the way that I personally think about these things. Here's what I keep in my head. I'm going to tell you my way now, not the author's way. When is it a function? A relation is a function if anytime the inputs are the same, the outputs are the same.
Right.
If you give it the same input, you get the same output. So h breaks this, because with h, I can give it, or sorry, not h, g breaks this, because the same input, where is it? The same input goes to two different outputs. So g here was not a function.
Right.
So it's a function if having the same inputs means the same outputs. It's a one-to-one function if having the same outputs means you have the same inputs.
Sweet. Okay.
Now, going to quickly show you that a function being one-to-one is logically equivalent to its inverse also being a function.
That
Make
makes sense.
sense?
Yeah.
So, just quick proof. Let's run through it. F is one-to-one if and only if its inverse is also a function.
Okay.
So I'm going to go the forward direction first. I'm going to show that if f is one-to-one, if it has this property, then its inverse is a function. And then I'm going to show if the inverse is a function, then it has this property. So start out. Let f be one-to-one, meaning let it be a one-to-one function. And let x and y be two things in the domain of f, such that they have the same output. So whatever x and y are, they give you the same output.
Okay.
Good so far?
Yeah.
Now, what does it mean for a function to be one-to-one?
It means that if they have the same output, they have the same input.
It means if they have the same output, then they must have had the same input. So since f is one-to-one, I knew f of x was equal to f of y, and so since f is one-to-one, then x must be equal to y. You with me? So now I need to make sure that f inverse, what am I trying to prove? I'm trying to prove f inverse is a function. That's what I'm trying to show. How do I show f inverse is a function?
You have to
I need to show if you give it the same inputs, it gives you the same outputs. So now I'm going to plug in to my f inverse function, f of x.
Okay.
What is f inverse of f of x?
Just check. Just
That's x. What is f inverse of f of y? Y. So this is my output to my inverse function, x and y. And how are x and y related?
the same.
They're equal to each other. How did we know that? From up here, from the fact that's a one-to-one function.
Gotcha.
So since it was one-to-one, the outputs of your inverse function were equal. And so equal inputs led to equal outputs with our inverse function. So our inverse function is, in fact, a function.
Sweet.
Our inverse relation is, in fact, a function. Probably a better way to say it. Now let's go the other direction. Let's assume that we have f, here's a function, and f inverse is also a function.
Okay.
And once again, let x and y be in the domain of f, where they map to the same output.
We're trying to prove that f is 1-to-1.
This time I'm trying to prove it's one-to-one.
Okay.
To prove that's one-to-one, I need to show the same output leads to the same input. So I grab x and y. I have no clue if they're equal to each other or if they're different from each other. But whatever they are, when you run it through the function, you get the same thing. So they have the same output. I need to prove now that x is equal to y. That would mean it's 1 to 1.
Is that x, y is supposed to be in the domain of f or in the domain of f inverse?
The domain of f.
Okay.
Because I'm trying to show that f is 1 to 1. How do I show that f is 1 to 1?
We show that if they're outputs.
I need to show that anytime you pick two things that have the same output in f, those inputs were in fact the same. So I care about inputs for f.
Okay.
So I care about the domain of f. So let x and y be in the domain of f such that they map to the same thing. Whatever it is. Then, what is f inverse of f of x? X. And what's f inverse of f of y? Y.
So x is equal to y.
So, I knew that f inverse was a function, so whatever I get when I plug in this is the same thing as what I get when I plug in this. Because those two were equal to each other. So plug in the same thing to a function, and the result has to be equal. And what is the result of this? Y. And what is the result of this? X. So I knew this portion of the equality, I knew that this was equal to this because f inverse is a function. And so plugging in the same input means getting the same output. And the output to this happened to be x, and the output to this happened to be y. And so I got x was equal to y. So I showed if the outputs to f were the same, then the inputs must have been the same.
Is it always given that we have a function where two different numbers will lead to the same output? Or are we just assuming that? Like, is that a fair amount?
I grabbed two random things in the domain, maybe the same thing, maybe the different thing. All I required is they have the same output. So yes, you can always satisfy that because you can always, assuming you don't have an empty domain, but if you have an empty domain, it's still vacuously satisfied.
Right, okay.
But yeah. Okay, therefore f is 1 to 1. So showed if it's 1 to 1, then its inverse is also a function, and showed if its inverse is a function, then it's 1 to 1. Strongly recommend you also go and read the author's proofs from your book for these. I did it different from him. So now you can see it two different ways, and hopefully wrap your head around it. Should probably stress, since you guys don't think I stress it enough, I strongly suggest you read your book.
Very good book.
Make sure we get that on camera for when we try changing history down the road.
Stop. Don't make fun of me.
I always will a little bit. That's just part of being in the class. Okay. So, there we go. Next one. Odds are you came across 1 to 1 before in your algebra class. And when you came across 1 to 1, you also came across on 2 was the other one.
Yep.
So what exactly is on 2? Remind ourselves what this notation says. F is a function from A to B. What do I know about F?
The domain of it is A.
The domain of it is A, and the image of it is a subset of B. So remember the way, I told you I'm going to say this 1,000 times. This says F maps everything in A to something in B. But it didn't have to use all of B. Here was our example not using all of B, just some of B. It can use all of B, or it can use just some of B. If it's the case that it happens to use all of B, then we say it is on 2.
Okay.
So, a function from A to B is on 2 if the image of F is all of B. So if this were my A and this were my B, F is not on 2 because it did not use all of B. If this were my A and this were my B and this is my F, then it is on 2 because it did use all of B. That's all it means.
Where does that word come from? On 2? Why do we use
I'm not sure the choice behind that definition.
Weird. Okay.
But that's what it means to be on 2. It means that the image of F is the entire right-hand set. That's all it means. Okay, and now if a function is both 1 to 1 and on 2, then we call a bijection. So a function f from A to B is a bijection if it's 1 to 1 and on 2. Good? Okay, so let's do a bunch of proofs now, small proofs, just to get you comfortable with all this. So our first proof here, I'm going to prove that the function f from the integers to the integers, that's not going to work. Let's give me b rationals. You okay with rationals? Or maybe reals, let's not confuse you. Just one that you would have seen in your algebra class a bunch of times. Okay, we're going to prove that the function from the real numbers to the real numbers by f of x equals 3x plus 4. 3x plus 4 here is a function you've seen 100 times. What does it look like? Just to graph it to make you feel good about it. Well, its y-axis is 4, or its y-intercept is 4, 1, 2, 3, 4, here it is, and it has a slope of 3. So it goes up 3 over 1, up 3 over 1. Very roughly, this is what we're talking about, this function. Intuitively, what does it mean for it to be a function? Or sorry, going back to your algebra course, what was your test for a function? You have what you call the vertical line test. If a vertical line only intersects at one point, it's a function. And if a horizontal line only intersects at one point, it's 1 to 1.
Yes.
Here's an example of a function that's not 1 to 1, a parabola. Because what does, if this is 4, 4 comes from both 2 and from negative 2. So it doesn't cross a horizontal line test. So it's a function, but not a one-to-one function, reminding you of some of your more pictorial tests from grade school. Now, what does it mean for it to be a bijection? It means it's 1-to-1, which this is. It passes your horizontal line test. And it's on 2, meaning that its range is all real numbers.
Which it is here.
Which in this case it is. All the outputs, all the y values, is going to be every real number. Top to bottom, you're going to get everything to come out of this function.
Right.
Okay, so now we're going to prove that using more precise definitions than just getting intuition for what the picture's saying. But that's the function we're talking about. Good intuition so far? Okay, so let's go ahead and write the proof. So let f from R to R by f of x equals 3x plus 4. I'm proving it's a bijection, so I need to prove it's 1-to-1 and I need to prove it's on 2. Doesn't matter which way we do first. Let's go ahead and prove it's 1-to-1. How do I prove it's 1-to-1?
Show that if the outputs are the same, the inputs are the same.
I need to show that if the outputs are the same, the inputs are the same.
Yes.
So pick 2 random things out of the domain. So let x and y be in our domain. In this case, it's the real numbers.
Right.
Let x and y be any 2 real numbers you want, such that f of x is equal to f of y. So I don't know what x and y are. All I know is that when you run them through the function, they give you the same value.
And you can just algebraically prove that.
Yeah, you're going to then just make reference to whatever your function is to prove this always.
It's super easy.
So it's super easy once you understand what you're doing. So 3 then, what is f of x equal to? 3x plus 4.
That's equal to 3y.
That's what you get when you plug x into the function. What do you get when you plug y into the function?
3y plus 4.
3y plus 4. Everyone follow that? Maybe using the x and y here is a bad idea. Let me pick different variables just so that you don't get confused with the fact that we use x when we define the function. So I'm going to say let little a and little b be in the real numbers such that f of a is equal to f of b. Maybe that's a better way to do it. So I picked 2 real numbers that happen to map to the same thing in this function. That's all I know about it. I need to prove that those 2 numbers were actually the same number. I need to prove a is equal to b. So what is f of a? What do I get when I plug a into this function?
3a plus 4.
I get 3a plus 4. You with me? So then, I know that 3a plus 4 is equal to what? Whatever I get when I plug b into the function, 3b plus 4. With me? Subtract 4 from both sides, and what do I get? 3a is equal to 3b. Divide both sides by 3, and what do I get? A equals b. Perfect. So I just really showed if their outputs are equal, then their inputs are equal. That means that this function is 1-to-1. So I showed that the function is 1-to-1. Now I need to show it's on 2. How am I going to show the function is on 2? I need to say that it will give you any output you want. So you pick any number you want. I need to tell you how to get that number.
Okay.
Give me a concrete case. What's the number you want me to make this spit out?
-5.
You understand what I'm saying? I'm telling you that this function can spit out any number. Pick any number you want, and I can find an x to plug in that spits out your number. That's what it would mean for this to be on 2. It spits out every possible real number. And so he said, make it spit out -5. So I'm going to show you how to make this spit out -5. With me? So I say plug in -3. Notice, what's 3 times -3? -9. Plus 4 is -5. So I found a number that happens to spell out -5. He says, okay, well, what about 100? I say for 100, plug in, let's say for 101, it's easier. For 101, then you plug in 29. Did I do that right? No, I did that wrong.
That's low.
Oh, I was still thinking weird. Oh, stick with 100. 100 minus 4 is 96. Divided by 3 is 32. Okay. So how do I make it plug in 32? What's 32 times 3? 96 plus 4 is? So for any number you choose, I can find a number that spits out your number. Now I need to prove that I can do that. I can't just say it.
Right.
With me? So now I need to say, for let, this time I'll let b be any real number. And now I need to find the a that maps to b. Let b be any real number, comma, and observe that a equal to b minus 4 divided by 3 is a real number. If I take a real number and I minus 4 from it, it's still a real number. And if I divide it by 3, it's still a real number.
We know that division is closed on the rails.
Division is closed on the rails as long as you're not dividing by 0. Yes, you know that.
Right. It's not closed on the integers. Though.
No.
Okay.
But we're on the rails, so we're good.
Right.
Okay. So, 5. Then, what is f of a? F of a is f of b minus 4 divided by 3.
Which is b.
Which is equal to, let's plug this in. b minus 4 divided by 3, plug that in for x. That's going to be 3 of b minus 4 over 3 plus 4, right?
Yep. 3's canceled.
Canceled 3's out top and bottom. So this is equal to b minus 4 plus 4 is equal to b.
I love that.
And so 6. Therefore, f is on 2. Which then gives me into bijection. Because we have both.
Right.
Square numbers. Sorry, running out of space. So how did I show it was a bijection? I showed it was 1-to-1 and I showed it was on 2. Now, hopefully all this makes sense for you so far, but it might be a little mysterious to you. How did I come up with this a? How on earth did I come up with that?
You solve for x.
So I looked at this function. This function is adding 4, or sorry, it's multiplying by 3, then adding 4. So I did the function that first subtracts 4, then divides by 3. Now there's a systematic way to calculate these, and it's the exact same way that you calculate an inverse function in your algebra classes. So let's see exactly how I did this, and how you can do it in any function. You remember calculating inverse functions in algebra?
No, we never did that.
You never did it?
Actually, I don't remember ever.
Okay, so let's write out this function as y is equal to 3x plus 4. Same thing we were working with.
I do actually remember doing that part of that.
Now, what does an inverse do?
Swaps your.
When we take an inverse, we just swap all our elements.
Right.
Or we swap our x's and y's. So now, if this is your function, the inverse function is going to be what you get when you swap the x's and y's. So your inverse function is going to be x is equal to 3y plus 4.
It's coming back to me. That makes sense.
That's it. That's all you do to get your inverse function is just swap your x's and y's.
And then
And now just solve for y. subtract 4. So I'm going to get 3y is equal to x minus 4. So I just moved the 4 to the other side, but I also swapped the order I'm writing in because I want my y's on my left. But I just subtracted 4 from both sides. So 3y is equal to x minus 4. And now divide both sides by 3. I get y is equal to x minus 4 divided by 3.
Yep.
That's what I was doing in my head to calculate this really quick.
So that's where it came from.
That's where it came from. And so that's where this suddenly came from.
Right. That makes sense.
Good? And that's how you calculate inverse functions, when you have to calculate them by hand. Very simple. Just swap your x's and y's. That's all an inverse is doing. Any questions on that? Let me make it very clear. You are going to be doing these proofs. I'm going to be giving you a function like this and saying prove it's 1 to 1 and on 2. You'll be doing that on your homework. You will be doing that on your test next week.
Next week? The week after next, isn't it?
Yeah, but next week sounds scarier, so maybe we'll pay attention.
I am paying attention.
You are. That's good. So, you need to make sure you understand how to do this. So if any of that is scary, let's do more examples until it feels not so scary. I guess I have another one up here, so let's do the next one. But if you want to see more examples, let's do more examples. So for our next one here, we're going to do this proof now. This time I'm going to prove that it's not 1 to 1. So we proved that this one was 1 to 1. What about when it's not 1 to 1?
You should find a counterexample. It's super easy.
Yep. So prove that f from the integers to the integers by f of x equal to x squared is not 1 to 1. Okay, 1. We're going to start with just let f be that thing. Let f from z to z by f of x is equal to x squared. We are going to prove that this is not 1 to 1. If it is not 1 to 1, what am I saying? I'm saying it is not always the case that just because the outputs are equal, then the inputs are equal. I'm going to prove that that is not the case. 2. Observe what is f of 2? What do I get when I plug 2 into this function?
2 squared.
2 times 2 is just 4. Plug in 2. 2 times 2 is 4.
So you're just putting 2 in for
Uh-huh. I'm basically saying what is 2 paired with in this function? Remember, we wrote this function out explicitly all the way over here. Here it is. What was 2 paired with? 4. It's just a function, f of x equals x squared. That was a pattern. What is the left-hand element of x, x squared? What is the what is the right-hand element of x, x squared? What is the right-hand element of 2? 4. What is the right-hand element of negative 2? 4. So notice that f of 2 is equal to f of negative 2. They're both 4. You with me so far? But 2 is not equal to negative 2. So I found a case where f of x is equal to f of y, but x was not equal to y. They were different numbers. So it is not the case with this function. It is not the case that just because f of x is equal to f of y, that x is equal to y. Or in other words, I found 2 different numbers that map to the same thing. If a function is 1 to 1, you can't find 2 different numbers that map to the same thing. Because no 2 different numbers map to the same thing. Every different number maps to a different thing. That's what it means to be 1 to 1. So that's how easy it is to prove that it's not 1 to 1. Similar for on 2. If you're proving a function is not on 2, you just find a number that can't be spit out.
Right, okay. That makes sense.
Should we prove that this one's also not on 2?
Oh,
Not 1 to 1.
I see how that works, okay.
And not on 2. So far we showed this is not 1 to 1. Okay, now it's for show it's not on 2.
And all we have to do is like try to get it to spit out -1 or something.
Well, show that I can.
Right.
Observe that x squared is always greater than or equal to 0, which means f of x equal to x squared equal to -1 has no solution. So you can't ever get to spit out -1. So we found something it can't spit out.
In the reals, right? Or letters.
We found an integer it can't spit out, namely -1.
Is this function bijection or not bijection? Is this function onto if you give it the domain?
If we change our codomain here, then yeah, you can force it to be on 2. You can always force it to be on 2 by just replacing it with whatever the image of the function is.
I mean, if we made our domain complex numbers, and so we have solutions to,
We're not even going to go down that road.
would that make it onto though? Or 1-to-1? I mean, or either not 1-to-1.
No.
Would that make it onto?
Were to make it on 2, could you get every complex number? My gut is no, but I'd have to think about it. Anyways, that's how you prove it's not on 2. You just find up with one output that can't be generated. Okay, let's move on to our next example. Let A be the set of all evens and B be the set of all odds. That's what I'm saying there. I didn't want to write out exactly what it was. We're going to prove that the function from A to B by f of x equals x plus 1 is a bijection. So I'm going to prove it's both 1-to-1 and on 2. With me? Okay, so proof of whatever we have written right there. Not going to rewrite it out. Okay, 1. Let A equal the set of evens, B equal the set of odds, and f be a function from A to B by f of x equals x plus 1. With me so far? Just setting up the problem. Now I need to prove that it's 1-to-1, and I need to prove that it's on 2. So let's start with 1-to-1. How do I prove that a function is 1-to-1? I need to show if the outputs are the same, the inputs were the same. So now I need to say, let A be in our domain set, pick 2 things out of the domain, in this case it's A, such that f of A is equal to f of B. So pick 2 things in our domain that map to the same thing.
Okay.
I need to show that A and B are equal to each other. Now what do I know about A?
It's an even.
It's an even. And what do I know about B?
It's odd.
It's also an even. They're both from set A.
Oh, oops, sorry. Yes.
Okay, so if A is odd, what do I know?
If A is even,
Or sorry, if A is even, what do I know?
you give it 2 times.
It can be written as 2 times something. So I know that there must exist m and n in the integers such that A is equal to 2m and B is equal to 2n. That's what it means for them to be even.
Oh, cool, that's how it works.
Okay, 4. What is f of A equal to?
2m plus 1.
Then f of A is equal to 2m plus 1. What does f do? It just adds 1 to whatever you plugged in. So f of A is equal to, maybe be more explicit, it's equal to A plus 1. But A is equal to 2m, so that's equal to 2m plus 1. Just plugging A, whatever f of A is.
Right.
Similarly, what's f of B?
It's 2n plus 1.
F of B is equal to, when we plug B into our function, remember, maybe you can't see the function too well here. Our function is f of x equals x plus 1. That's what our function does. It just adds 1 to whatever it is. So f of B is just b plus 1. But I know b is even, so b can be written as 2m plus 1. With me so far? I'm trying to show A is equal to B. I know f of A is equal to f of B. I'm trying to show A is equal to B.
Right.
Oh, I didn't even need to use the fact that these are even or odd. I'm way overdoing this.
Yeah.
So, forget all this. Sorry, that was overkill. And probably just gonna do more to confuse you than help you. So let A and B be in A. I know f of A equals f of B. What is f of A?
It's 2A.
2A plus.
F of A is just A plus 1.
Oh,
And what's f of B is just B plus 1.
sorry.
So then I know A plus 1 is equal to B plus 1. If f of A is equal to f of B, then A plus 1 is equal to B plus 1. Because A plus 1 is f of A. It's what you get when you plug A into F.
So F is equal to B.
And f of B is B plus 1. It's what you get when you plug B into F. Subtract 1 from both sides, and I get A is equal to B, which gives me F is 1 to 1. I showed if the outputs are equal, then the inputs were also equal.
Right.
Okay, that was the easy part. We didn't have to use any even or odd to think about that. Okay, 4. Now I'm trying to show it's on 2. How do I prove a function's on 2?
Any input.
I need to show for any output you choose, I can find an input to plug into the function to give that output.
Right.
So you can pick any odd you want. I need to show you the even that will map to that odd. You with me?
Mm-hmm.
Okay, so now what variable should we use? Y for the output?
Sure.
Let Y be anything in B. My job is to now find something that will map to Y. So Y is anything in B. Pick anything you want. I'm going to find something in A that maps to that B. That's what it means to be on 2. We use all of B. We map to everything in B.
The Y here is just equal to like
Now, if Y is in B, what do I know about Y?
odd.
It's odd. So that means, what does that mean? What's the definition of odd?
It's equal to 2 times the integer. plus
There
1.
exists some integer m, whatever. There exists m in B such that Y is equal to 2m plus 1. That's what it means for Y to be odd. With me?
Okay.
5. Let x equal sorry, excuse me. Let x equal 2m. What do I know about x now?
It's even.
It's 2 times an integer, so it's even.
So it's in A.
So that gives me that x is in A since it's even. And what is f of x equal to? If I plug in this x. Sorry, I probably shouldn't have used an x. Does it confuse you when I do that?
No, it's
No.
fine.
Okay, so what do I get when I plug x into this function? X is 2m. What do I get when I plug 2m into this function?
2 plus 1.
Just 2m plus 1. The function just adds 1 to whatever you have. So f of x is equal to x plus 1, but x is just 2m, so it's equal to 2m plus 1. And what is 2m plus 1?
It's not.
It's y,
Y. Yeah.
which is equal to y. There you go. I found the x that gives you the y.
It's like.
Now this is pretty obvious what I did here.
It's really simple. Yeah.
Pick a concrete example. Give me an odd number.
9.
9. Using this function, what's the even number that maps to 9?
8.
8. It's just the same thing minus 1.
Right.
If you gave me the odd number 101, what's the even number that maps to 101 using this function? 100. So what was the x? It was the y, except for without the 1. It was just y minus 1. That's what mapped to y.
Very simple.
Very simple, but using definitions that might make it a little bit confusing on how you prove it. Good?
Yeah.
Okay. So that was functions. Now we move on to function composition.
Well, flashbacks.
Oh. Little late.
Yeah.
See if I can get the whole board so I don't have to worry about going off. Okay. Function composition. What is function composition in a nutshell? It's combining two functions into one function. That's all it's doing. So let's go through a very concrete case before we go over the definition to hopefully make it very clear. So we're going to let A be the set 1, 2, 3, 4, 5, and I have it pictorially drawn right here. B be the set 6, 7, 8, 9. I have it drawn right here. C be the set 10, 11, 12, 13, 14. Sorry. 14 included as part of it. Trying to make it very pictorial, very obvious what's going on here. F is going to be a function from A to B. Here's F. G is going to be a function from B to C. Here's G. So let's draw it out really quick. So F is this exact function. So what does it map 1 to?
6.
6. What does F map 2 to?
6.
What does it map 3 to?
9.
What does it map 4 to?
7.
What does it map 5 to?
Also 7.
Okay, so there's what F does. So notice F is a function from A to B. G is a function from B to C. What does it map 6 to?
10.
What does it map 7 to?
11,
What does it map 8 to?
12,
And what does it map 9 to?
13.
13. So notice F maps everything in A to something in B, and G maps everything in B to something in C. Now, you can think about this as you just following these paths. If you were here at 1 and you followed the path, where would you go? Start at 1 and you would go to 6, and then from 6 you go to 10.
Yeah.
Doing both functions. If you started here at 3, what would you do? You come down to 9 and then over to 13. That's all function composition is doing. It's going through both functions instead of just one. That's it.
Makes sense.
So, one thing that confuses students about functions, when we look at G composed with F, you do F first and then G. This is saying go through F, then go through G.
So you're taking
Some people read this as G after F. G composed with F, G after F.
same thing.
Same thing.
So we're taking the output of F and putting it into G.
Right, so we follow F, then we follow G. So starting with 1, when we take 1 and we run it through F, where do we go?
We go to 6.
And then where do we go?
10.
So, when we do F then G, 1 went to 6 and then to 10, and so it ended at 10. Where did 2 end?
And also
10. Where does 3 end?
13.
13,
Where does 4 end?
11,
Where does 5 end?
Also 11.
That's all function composition is. Do one function, then the other. But you read it right to left. You do the right function first and then the left function.
Are we always guaranteed that the composition function is a function?
No, you can't just compose any two functions together that you want. Because G has to start where F leaves off.
Okay. So they have to have G's domain.
So if we tried to instead do F composed with G, if we instead tried to do F composed with G, and see what that equals. So let's see, we're starting with G, where would 6 go? Well, 6 when you run it through G goes to 10, and then where does F take 10?
It does, it's not displayed.
It doesn't. And so this doesn't work. So you want the special case where F ends, G begins. So now let's go over function composition, and hopefully this makes sense. Let A, B, and C be sets, just like we have here, A, B, and C. Here's a concrete example. Such that F is a function from A to B, and G is a function from B to C. Very important that G picks up where F leaves off.
They have to have the exact same.
If G starts in set B, that has to be where F ends. Otherwise, we can't do both of the functions. So very, very important. If I'm composing F with G, wherever F ends,
G has to begin.
G begins. In order if we're going to combine them this way.
Right.
So then, if you have this case, then G composed with F is a function from A to C. It starts with A. Notice that when we did both functions, we started at A and we ended at C. G composed with F, all its inputs were in A and all its outputs were in C. So if f was a function from a to b, and g was a function from b to c, then g composed with f is going to be a function from a to c. Because it's just doing both.
Right.
Am I losing you?
Slightly. I'm sorry.
Okay. Say this one more time. Our function f here takes things from a, set a, and maps them to things in set b.
Yeah.
That's all it does.
Yeah.
Our function g takes things in set b, maps them to set c. What did g composed with f do? Where did it start? It started with a. Where did it end? C. That's all we're saying. So let a, b, and b, c be sets. F took us from a to b, and g took us from b to c.
Okay.
Then g composed with f was a function from a to c. Good? And now here's its definition. By g composed with f of a is just g of f of a. That's how you actually compute one of these.
Yeah.
Let's run through this.
That makes sense.
So using these exact functions we have up here, we're going to look at g composed with f of 4. I'm plugging 4 into this new function. Okay? By definition, that is just g of f of 4. You see this? You always just replace with that. Good so far? Now looking up there, what is f of 4?
It's 7.
F of 4, what is the right-hand element of 4 in f?
7.
7. Or what does f map 4 to? 7. And then what's g of 7?
11. That's 11.
11. So, g composed with f took 4 and mapped it to 11, which is exactly what you said here. 4 went to 11. This is just how you compute it now.
Okay.
Function composition. So, let's do some examples writing out function composition. So I've got f is a function from r to r by f of x equals x squared plus 1. G is a function from r to r by g of x is equal to 2x minus 1. Can I compose these two functions together? I can compose them together if one function ends where the other begins. Where does r end? Or sorry, where does f end? In r. Where does g start? In r. So I can compose g to f. I can do g after f. And vice versa. This one, it happens to be the case I can go both ways. I can do g first and then do f after. Because I just kept using the same set over and over again. We didn't have A, B, and C as different sets. This time we kept using the same set over and over again. All right, let's run through it. And let's run through it in just the case of 2. So what is G composed with F of 2? By definition, this is just G of F of 2. With me so far? That is just using the exact definition. What is G composed with F of A? It's G of F of A. That's its definition.
Right.
Okay, so now what is F of 2? What do I get when I plug 2 into F? 2 times 2 is 4 plus 1 is 5. So F of 2 is the same thing as 5. So this is just G of 5. What do I get when I plug 5 into this function? What is G of 5? What do I get when I plug 5 into this? That's 2x minus 1. Sorry.
Oh.
Now my marker's warmed up some. It will show up a bit better. 2x minus 1. So what's G of 5? 2 times 5 is? Minus 1 is? 9. You follow that? Okay, that's it. Let's try F composed with G of 2. So we change the order here.
Okay.
What is that by definition? That is just F of G of 2. What do I get when I plug 2 into G?
3.
2 times 2 is? Minus 1 is? So this is the same thing as F of 3. What is F of 3?
7?
9.
No. 10, sorry.
10. Yeah, that's x squared. So that's just 10. So f composed with g of 2 is 10. G composed with f of 2 is 9. Notice that the order you compose in matters.
Yes.
Or in other words, function composition is not commutative. Okay, now let's do it for functions in general. What is g composed with f of x now, rather than just 2? This is still the exact same thing as g of f of x.
So the starting letter is the formula we use?
So
It's just going to be the first function inside the second function. I don't know how you want to read that, but that's just its exact definition looking at this. If you have g composed with f of a, that's g of f of a. Similarly, if I would have had f composed with g of a, this would have been f of g of a. So whatever the order is on your functions here is the order on your functions here. So if that makes sense, yes.
I was more asking, so the letter, I guess, that is shown first in the thing is the formula we use.
Oh,
Like,
yes.
G is first, so we use.
G is to the left, F is first. Remember, first is going right to left.
Oh,
That will come back to bite you. But if you write it this way, once you write it this way, I think you're okay. Because now, what is f of x? So this is g of f of x. But what is f of x?
X squared plus
X squared plus 1. So far, just replace f of x with whatever f of x was.
okay.
Okay, now I'm going to plug x squared plus 1 into g. So that is going to be 2x squared plus 1 minus 1. Plugging x squared plus 1 into g.
Okay.
See it?
Yeah.
And now that's equal to 2 times x squared is 2x squared. 2 times 1 is 2, minus 1 is just plus 1. You with me? So that is what g composed of f, g composed with f of x is. It's 2x squared plus 1.
Okay.
Now notice what we did down here. We plugged 2 into this. What do I get when I plug 2 into this function?
get 2 squared for 8. Give me
16?
Almost.
17.
You multiply by an extra 2. 2 times 2 is 4, times 2 is
8.
2 squared. We're plugging 2 in.
Yeah.
So 2 squared is
Oh.
4, times 2 is 8, plus 1 is
9.
9, which is exactly what we knew it should be. G composed with f of 2 is 9. When I put 2 into that function, I should have got 9. Here we slowly did it by hand for a concrete case. Here's what it is in general. So now you don't need to go re-plug through every time. If I were to ask you what's G composed with f of 5, you don't need to re-plug it in and think it through. Just go straight to this. It's going to be 51, and I don't need to re-think through all that. So here's what it is in general. Here's what it was in the special case of using a 2. Now let's look at f composed with g of x. What is this going to be? This is going to be f of g of x, by definition. Now, what is g of x?
It's 2x plus 2x.
G of x is 2x minus 1. Now I'm going to plug 2x minus 1 in up here, into f. So this is going to be 2x minus 1 squared plus 1, which is equal to, I don't know if you guys are okay with doing these quick now.
It's 2x squared.
Are you guys okay with me going straight to 4x squared minus 4x plus 1 for this,
Yeah. Plus 1. Plus 1.
and then plus 1 again?
Okay. So that's just.
So this was expanding that out, and then that plus 1 is that plus 1. But that's just doing the algebra. You could have factored it. That's the way it comes out. And then this is just equal to 4x squared minus 4x plus 2, combining the 1 and the 1. Once again, notice, what do I get when I plug in 2 for this? 2 times 2 is 4. 4 times 4 is 16. So this is 16 minus 8 is 8 plus 2 is 10. f composed with g of 2? 10. So here's what it is in general. Here's what it was for the concrete case of 2. That's function composition. Good? Okay. Couple easy proofs and then we're basically done. Note, we already said it, but I'll say it again. Function composition is not commutative. It matters what side they're on. Addition is commutative because 3 plus 2 is the exact same thing as 2 plus 3. You can swap what sides of the plus you're on and it doesn't change anything. Function composition is not commutative. G composed with f is not the same thing as f composed with g. They're very different things. So don't accidentally do that with your functions. Now we're going to prove that function composition is associative, which means you can put the parentheses wherever you want. So let f be the function from a to b, g be the function from b to c, and h be the function from c to d. So I got 3 functions here. Notice that f goes from a to b, g can then take it from b to c, h can then take it from c to d.
Okay. Yep.
Okay. So I'm going to prove that h composed with g composed with f is the same thing as h composed with g composed with f.
It is.
So I can compose g and f together first, and then compose with h, or I can compose h and g together first, and then compose with f.
Okay. Oh,
So,
that makes sense.
Going to prove that these 2 functions are equal.
Okay.
With me so far? What does function composition do? G composed with f, it combined 2 functions together into just one function, one mapping. Rather than going from a to b and then going from b to c, G composed with f went straight from a to c. So over here, f is going to be a function that takes you from a to b. G is a function that takes you from b to c. H is a function that then takes you from c to d. So what are we doing? A, b, c, d. Here's our sets. F is going to take us from somewhere in here to somewhere in here. G takes us from somewhere in here to somewhere in here. And then H takes us from somewhere in here to somewhere in here. That's what the functions are doing.
Is there any mathematical reason why they have us read it backwards? No, like genuinely, is there a reason, or did someone just want to seem smart?
No, the reason is because of how it's defined here. You do your inner function before you do your outer function. So your most inner function is closest to your term. Your most outer function is furthest away from your term.
So if you read it from left to right, it's kind of like the further right you go, the more inside you get.
So now, what is G composed with F? G composed with F is combining these 2 functions in one go and just going straight like this. This would be G composed with F.
Yep.
With me? And finally, what is H composed with G? H composed with G is going straight from here to here. And so what we're saying is, if you do H after G composed with F, so G composed with F takes me from here to here, doing that and then doing H is the exact same thing as doing F first and then doing H composed with G, which is this. So this one is saying, first do G composed with F, that's saying take this route, and then do H, which gets us here, is the same thing as doing F first, and then doing H composed with G, which is this top arrow. That's what it's saying. And that's what we're going to prove. Does that make more sense? Okay. Now, how do you prove 2 functions are equal? To prove that 2 functions are equal, you need to show 2 things. 1, that they have the same domain. 2, that for any input in the domain, they map it to the same location. So two functions are the same if they both map the same elements and they map them the same way. Let me give you two functions that are not equal but are mapping the same way. Say I do f is the function that maps 0 to 1, 1 to 2, and 2 to 3. Or in other words, it just adds one to the function, the left-hand term. If I then make g the function, 0 to 1, 1 to 2, 2 to 3, 3 to 4, these functions are not the same thing.
Right, okay. But they map something.
They map the same way. Whatever this maps 0 to, this maps 0 to. Whatever this maps 1 to, this maps 1 to. Whatever this maps 2 to, this maps 2 to. But this is missing a term that this one has.
So if you prove that they're both mapping,
So if I prove that they have the same domain, if they have all the same left-hand elements, or in other words, this one also had 3, and then I also show for any left-hand element they pair it the exact same way, so this one also pairs it to 4, then the functions are equal.
okay.
So to show functions are equal, you need to show two things. They have the same domain, and they map the same way.
Right.
They pair numbers the same way. So it's not enough to just say they pair numbers the same way, because maybe they aren't using all the same starting numbers. So they need the same domain, and they need to pair the same way. So I am going to prove that these two functions are equal to each other. So, one, let blah, blah, blah. Let f be a function from a to b, g be a function from b to c, h be a function from c to d. Okay? There's my let. 2. Then, what is the domain of h composed with g composed with f? When you compose two functions together, then the domain is the domain of the left-hand function. When I did f composed with, or g composed with f up here, g composed with f, where did we start? We started at A. We started wherever f started. So the domain of your composition is just the domain of your right-hand function, the one you do first. And so the domain of h composed with g composed with f is going to be equal to the domain of our right-hand function, which is g composed with f.
Which is C.
And now, what is the domain of g composed with f?
C.
It's just equal to the domain of f. Well, take it one step at a time to make sure you understand the thinking here. The domain of this function is the domain of the right-hand thing we're composing with.
You're right.
So it's the domain of the right-hand thing we're composing with. Now, what's the domain of this function? It's the domain of the right-hand thing we're composing with.
So it's A.
And what's the domain of f? By definition, f was a function from a to b. That's just set A. Similarly, what is the domain of h composed with g composed with f? By definition, it's the domain of our right-hand function that we're composing with.
F. So A.
So in this case, it's just the domain of f, which is also just equal to a. So this function and this function have the exact same domain.
Sweet, okay. Now
So we prove that.
Can we show they map the same now? Right.
So domain of h composed with g composed with f is equal to the domain of h composed with g composed with f. So show they have the same domain. Good. Now I need to show that they map the same way. So 3. Let little a be anything in our domain. Pick something that both those functions know how to map. And I may show that they map in the same way. Pick anything you want in the domain. I may show they map it to the exact same point. So the functions are equal. So let a be something in big A, little a in big A. So then what? What is h composed with g composed with f of little a equal to by definition?
It's H of G of F.
It's h of, maybe do square brackets here, it's h of the inner function applied to a, of g composed with f of a. Now, what is g composed with f of a?
It's G of F of A.
It's just g of f of a. So this is equal to h of g of f of a. I'm okay with you skipping straight from here to here if you want. But that's just using the definition and then using it again. Okay, so that's what it is. And what was h composed with g composed with f of a equal to?
The also H of G of F.
It's also just equal to, we would start out with, for this one, it would be h composed with g
Composed with F,
of f of a.
which is, okay.
And then once again, plugging that in, that is h of g of f of a,
Oh, they're the same.
which are the same. So 5, therefore, the two functions are equal. Because the output of this function for any input is that. The output of this function for any input, a, is that. And notice that those are the exact same symbols as those. So they're equal. Law of identity, everything's identical with itself. If that and that are the exact same symbols, they're equal. Good?
Yep. Cool.
Okay. So what's our next proof? Oh, we need one more definition, then we're ready for our next proof. An identity function on a set. So, pick a name for a set. Give me a letter.
A.
We use A a lot. We'll start with Bob.
Okay.
Bob is going to be our set. Give me some things to put in the set.
Triangle.
Triangle 2, 19, square. Okay, here's some random set Bob. Our definition for the identity function on a set. How do you write the identity function on a set? You write the letters ID and then the name of the set down low. Identity on Bob is equal to the function that maps everything in Bob to itself. So it's a function that maps triangle to triangle, 2 to 2, 19 to 19, and square to square. That's what an identity function does.
Pretty boring.
So once you have a set, the identity function just maps everything in that set to itself. Pictorially, so here's A. What does the identity on A look like? The identity on this set. It's a function that would take 1 and map it to 1. 2, map it to 2. 3, map it to 3. 4, map it to 4. 5, map it to 5. It doesn't really get you anywhere to run through the identity function.
Right.
You're back to where you started. Make sense? It doesn't do anything. It's identity. It doesn't change it.
Right.
Okay. So, now we'll read the exact definition. Let A be a set. Then the identity function on A is written as, well, right there, is written as ID and then the name of whatever your set is. If that was Bob, then we put Bob there. If it's A, you put A there. It's going to be a function from A to A, and it's just going to map little a to little a for every element little a in the set A. I don't know if I said that. For all little a in big A. So it just takes everything and maps it to itself. So another way you can write that, what is the identity function on big A? It's all the ordered pairs AA, where A was something in big A. That's it.
Sweet.
So that's an identity function. Just takes something and maps it to itself. So our next proof here is we are going to prove, let f be a function from A to B. Then we're going to show that f composed with the identity on A is the same exact thing as just f, which is the same thing as the identity on B composed with f. Now let's run through this intuitively. Let's pretend that this is our f. Here's A, here's B. So here's what we're showing are all the same. Let's see what happens when I follow this function. So first let's do identity on A. So I start at 1, and then where does identity on A take me?
1.
It maps back to 1. and then I do f.
So you get a 6.
That would have been the same thing as just doing f,
Yeah. Right, obviously.
which is the same thing as doing f and then the identity on b. What do I get if I do f then the identity on b? I start here, I do f, and then I do the identity on b, which just takes me back.
Yeah, it's almost trivial.
So identity function just maps every element to itself. So if I follow the identity function, I'm back to where I started. Okay, so let's prove that all these are equal. So I'm going to do proof. We'll say let f be a function from a to b. Then if we do f after the identity on a, that's going to be equal to f is going to be equal to the identity on b after f. I'm proving that those three functions are all equal to each other. How do we prove functions are equal to each other?
Show they have the same domain and map the same.
First you show they have the same domain, then you show they map the same. So, 1, observe. What is the domain of f composed with the identity on a? It's just the identity of the domain of the function we do first. So this is just the domain of the identity function on a. The identity function on a, what's its domain? A, because it just takes everything in a and maps it to a. So that's just a. Once again, what is the domain on just the function f? So we did the domain of this one. What's the domain of this one? That one's equal to a by definition. F was a function from a to b. What is the domain of the identity on b after f?
Also a.
It's going to be the domain of your right-hand function, f, which in this case is once again a. So they all have the same domain. Now I need to show that they map the same. So let, since they all have the same domain, pick something random out of their domain. Let little a be something in their domain. Okay? What is f composed with the identity on a of little a equal to?
It's f of the identity of a.
It's f of the identity on a of little a.
So it's f of a.
Right, and the identity on a of a is just a. It's a function that maps everything to itself. So what does it map little a to? Little a, just maps it to itself. And so this is just f of a. Similarly, what do we get when we plug a in for f? We get f of a. And then similarly, what do we get when we plug in identity on b composed with f of a?
The identity of b.
So maybe put f of a was also equal to f of a, and then this is equal to
The identity of b.
identity on b of f of a, which is equal to the identity on b. Whatever you give it, it just spits out our thing. So it's just going to spit out f of a. So they all get the same output. Therefore, the functions are equal. Now, our last proof. If f is a function from a to b, and it's 1 to 1, then f inverse composed with f is the same thing as the identity on a, and f composed with f inverse is the same thing as the identity on b. Let's think about an inverse function for a second. What does the inverse function do? It undoes whatever the function did. So that wasn't really a case. Let's have the case where we have a 1-to-1 and onto, or a 1-to-1 function. So A will say is a set just 1, 2, 3. B will say is a set 4, 5, 6. We'll say it maps 1 to 6, 2 to 5, 3 to 4. That's what f does. What is f inverse going to do? It's going to take 4, 5, 6. And it's going to map it to A, which will be 1, 2, 3. And it's just going to do the reverse. It's going to map 4 to 3, 5 to 2, 6 to 1. This would be f inverse. So if you do f and then f inverse, where do you get? Back to wherever you started. So if I do if I do f inverse of f of 1, what do I get? F takes 1 and maps it to
6.
6. Now plug that into F inverse, and it maps you back to 1.
Didn't we already use this in a proof over here?
Kind of. We use the fact that inverse undoes itself. But now notice that that 1 was something in A.
Yeah.
Okay, so that's what we're going to say. That would have been the exact same thing as doing the identity on A and plugging in 1. That will have also just given you 1.
Right.
So let's write out the proof. Scribble the proof right here, I guess. We'll keep that one in case we want to make reference to it for whatever reason. So this time, proof. Let me say, let F from A to B such that F is 1 to 1, right?
Yeah.
Then I'm proving that F after F inverse is what?
The identity on.
Identity on
A.
B.
B.
And F inverse after F is equal to
The identity on A.
identity on A.
Okay.
So that's what we're going to prove. Okay, so right out the door, going back to, oh, did I erase the proof?
Which one?
Where we showed that if a function is 1 to 1, then its inverse is also a function. Oh, that's it.
Yeah.
So right out the door, what do I know? I know since F is 1 to 1, comma, then F inverse is a function.
Yep.
And so given the same input, it has to give the same output. Okay, so now just keep that as a side note in mind for everything we're proving in here now. So now let's prove these functions are the same. This is equal to this, and this is equal to this. So first we need to show all the domains are the same. So observe that the domain of F inverse composed with F is equal to what?
It's the domain of F.
The domain of F, which is equal to A, because F is a function from A to B,
Yeah.
which is equal to the domain on the identity function on A. So those two have the same domain, comma, and I need to show these two have the same domain. The domain of F composed with F inverse is equal to the domain of F inverse is equal to F inverse maps from B to A now.
So B.
So is equal to B, which is also equal to the domain of the identity function on B. So that function has the same, this function, F composed with F inverse has the same domain as the identity on A, and this function has the same domain as that function. Now I need to show that they map the same. Observe F inverse after F, well maybe we need to pick something out of the domain first. So they have the same domain, so let's pick something out of the domain. So 3. Let little a be something in big A. That's the domain for these two functions. And little b in big B. Then, what is F inverse after F of little a equal to?
It's
If
F of inverse of F of A.
Perfect. F inverse of F of A.
Which is F of A gives you.
Which the inverse function just undoes whatever F did.
How do we know that?
That they undo each other.
Yeah. How do you prove that? Is that just a super?
We can write that out explicitly if we want. We could let A star be what A maps to, and B star be what B maps
I
to,
guess
but
it's just really obvious.
it's kind of obvious, and writing out explicitly
It's not worth it.
adds some messy notation, because we have to rename that thing.
It's just big, you know.
But so F inverse of F of A is just equal to A, which is exactly the identity on A of A. So So this function maps A to A, this function maps A to A. So they map the same way. Similarly, if we were to look at f composed with f inverse on B, that is equal to f of f inverse of B, which is equal to just B, which is exactly what we get when we plug in B to the identity function.
Sweet.
So they map the same way, and so they're the same functions.
Makes sense.
So to prove two functions are equal, what do you need to show? They have the same domain, and then they map the same way. Once again, I strongly recommend read the chapter. Re-go through these examples the way the author goes through these examples. To sit down and just watch me write it all out is very hard to just magically absorb. So this functions as a primer, so that when you go read the book and struggle through it yourself, you can hopefully make sense of what the author's saying and doing.
Or other way around.
Or preferably the other way around, but reading the chapter even before class I know is a dream.
I read it.
Oh, well, there's one.
I read it.
Okay, so that's it for today's lecture. A nice easy one to ease us into the second semester.
Yeah. I've seen this lecture like 5 times.
Okay, that also helps. You can always go rewatch and make sense of it again.